here in this workshop. And today I want to talk about how we have been using these quantum entanglement information tools, essentially entanglement measures, to detect quantum phase transitions. So first I would like to present my group there at the Chemistry Institute, but doing physics in Araraquara, UNESP-Araraquara. So at the moment, we have 4 undergraduate students, 3 PhD students, and 1 master. And we hope these 2 postdoctoral researchers will join us in the beginning of the year. And essentially what we have been doing there is trying to attack some many-body problems using mainly DFT calculations, dense functional theory calculations, also some exact methods. And in particular, we are interested in entanglement measures, exotic superfluidity, and quantum phase transitions. So here's the outline of the talk. I will give you a brief motivation of entanglement and the connection with quantum phase transitions, then talk a little bit about the specific model we have been using and the DFT calculations, and then present the results where I intend to show how the linear entropy and the von Neumann entropy may quantify very different things, at least in these systems. And I will show this for homogeneous, disordered chains, and superlattice systems, okay? So I like to start with the very basic thing, but the idea is that typically when we talk about entanglement or when we listen about entanglement, they are always related to some quantum technologies, quantum computers, quantum cryptography, teleportation, and so on. But now here I'm using entanglement as a quantifier of this quantum phase transition, as a witness for any quantum phase transition. That is the 4th example here. Because we expect that in principle, by varying a given parameter that drives that quantum phase transition, you should see some signature in this entanglement measure. So, and the reason for that is that, of course, we can define, for example, here, if you define 2 A-B parts that are entangled, we could consider that as almost anything. So it could be 2 particles, it could be spatial regions of your system. I will talk in a moment what kind of entanglement we are considering. But the main point is that entanglement is not a quantity that you have or not have in your system. Instead, you may have different degrees of entanglement. And this gives you the information that is necessary to try to treat or to try to witness quantum phase transitions. So these are the main thing here. So the idea is that then the degree of entanglement will be important for this issue, and also the fact that the entanglement measure may differ by varying a given parameter that drives the transition. Okay, so what we are doing here is trying to calculate a very specific type of entanglement. So I will start with the model, is the usual Hubbard model, where I just consider on-site interactions. And the external potential will be here used to map those disordered chains and the superlattice structures. And well, we know that this kind of model, despite the simplicity of this version of the Hubbard model, it's still quite useful for describing, for example, the attractive regime superfluidity, BCS, and unconventional superfluidity. And also in the repulsive regime, for example, if you combine with disorder, you could have this, what I'm calling here the Motte-Anderson physics and so on. So, but now, what kind of entanglement we are quantifying this specific system? So here we are considering this ground state average single site entanglement. And what this is exactly, we define a single site, so it's a spatial type of entanglement in the sense that we specify the site and trace the states, trace over these states, trace over the other L-1 sites, right? So when I do that, of course, it will depend pretty much on the choice of which site I'm using to do this measure, and that's why we do an average. So we vary the chain by doing this bipartite entanglement, calculating this bipartite entanglement in the per state. So such that I can use, for example, the von Neumann entropy as a proper measure for this quantity, for entanglement, right? So that's a bipartite entanglement of the ground state. And I do that by choosing then one side, tracing over the degrees of freedom of the remaining, and taking an average of that, right? So when I do that in the occupation probability basis, essentially, I can here write this, where this rho is the reduced density matrix of the single site, by the 4 possible probabilities, 4 possible states that I have there for each site, right? So it's just these W's here are just the probability occupation, single ones, double occupation, and zero occupation, okay? Well, then there in the quantum information community, there is a kind of belief that this entropy, this von Neumann entropy, is essentially equivalent to the linear one. And I will show you in a moment why they are pretty much related, of course. But the linear entropy is defined like that by the same reduced density matrix here. And they are a little bit different. I will show you in a moment how they are connected. But before that, I would like to show how these entanglement measures typically behave in these Hubbard models. And for that, I've chosen here 3 almost random results. We are working on that since 2017. And the idea here is just to give you a hint of what kind of signatures we typically look at when we analyze these entanglement quantities. So for example, here, I have the entanglement being quantified by the von Neumann, by the linear one. And this is the disorder strength. So I have the Hubbard model with a certain concentration of impurities there. So point-like impurities in this concentration. And what we see and associate to the localization phenomena here is the fact that from the 0 case to the almost any small quantity of disorder intensity here, this entanglement drops a lot for essentially half of the initial value. And then after that, essentially saturates for all the concentrations. So this saturation entanglement suggests that we have a pretty localized state. And this is one possible signature then. So and now here I'm comparing 2 different systems. I'm really in the attractive interaction regime. And I analyze a case where we expect to see a exotic superfluid phase, FFLO type. And what we see and use as a signature of the presence or not of this FFLO phase is the non-monotonic behavior of the entanglement with that driven parameter, in this case, the imbalance or polarization of the system. And here is the MOT signature. So this is how entanglement see the MOT transition when you go and reach in the Hubbard model n equal to the half filling, okay? So this decreasing, non-monotonic again, decreasing, and with this minimum there in the critical point expected for this phase. So now, how they are connected? Well, the linear entropy is just the linear term of the Taylor expansion of the log. That's why they are really mathematically connected. So if you just expand this here, and you consider just the first order term, then you end up with this expression, which is then given equal to 1, sum of all the possible states, all possible probabilities. And so it means between the von Neumann entropy and the linear one, I just have to consider the linear term of the log expansion here. So that's what I'm calling S1. So it's the von Neumann expanded to the first order. And our question now is, are the 2 quantities really measure or quantify, identifying properly these quantum phase transitions? Are they completely equivalent or not? And to answer this question, then we will use the Hubbard model in the homogeneous situation, in the disordered one, where here I'm defining this disorder as impurities with same intensity with a certain concentration randomly distributed in the chain, and also some superlattice structures where we have a periodic potential with some amplitude there. Well, for the homogeneous case, we know this is 1D Hubbard model, and we have the exact data, exact solution for that. But for this inhomogeneous case, the disorder in the superlattice one, we have to do some kind of calculations, and we have been using the dense functional theory to solve these inhomogeneous systems. So here I'm just giving a very general idea of the DFT. So essentially, we explore the Hohenberg-Kohn theorem that makes sure that there is this univoc relation between the wave function, the many-body wave function, and the particle density. And we also do the DFT in the constant scheme, so that means we treat our realistic system, interacting one, with help of this auxiliary system, which is the constant system, and so on. So here, essentially, we construct properly this effective potential that provides us the density of the realistic system. And, well, essentially, we end up then, when we define this effective potential, the constant potential, we can solve a Schrödinger equation of a single particle, where here are the constant orbitals, and we can calculate the density. But the point here is that this effective potential is also a function of the density. So we will end up in a self-consistent cycle. That means I have to start with some guess, initial trial here for the density, and then see whether I have converged or not, and so on. And if not, I can even use this output as an input, and so. So up to here, this method is completely exact. There is no approximation up to here. But the point is that for this effective here, I have to know, to calculate exactly this via this approach, I have to know the exchange correlation potential, what typically is not, in general, is not unknown. So how we do that for the Hubbard model then? We use this local density approximation. So we use what we know about the homogeneous system as an input in a local density approximation to extract information, then approximate it now for the quantities that we want in the inhomogeneous system, okay? So we do this LDA approach, and for that, by using this only, we have the energy and density profile. Now, for getting the entanglement, we do a similar procedure. So, but now for, oops, let me put here. But now for those two measures that I mentioned before, the von Neumann entropy and the linear one. So essentially, we use information for the homogeneous as an input, and then by plugging here and replacing the homogeneous density by the inhomogeneous one, obtaining this step, we have this, how to calculate these quantities, these entanglement measures for the inhomogeneous system. Okay, all of that to say that is an approximated method, but to give you an idea of how well this method performs, here just plugging some of our data where we are exploring very, very complicated systems with interaction and disorder and so on. And I'm comparing here these red dots are DMRG calculations, and the blue curve is the DFT. And sounds like we are having good results, even in this most basic LDA stuff that from the DFT community is pretty basic indeed, but in our case, it seems to work well. Okay, so since our results are reliable, I want to show you some of the results for this case. So first, we have considering the one in the Mott transition. So just in the homogeneous system, we have homogeneous chains, no disorder, no other potential, and these are exact data, not DFT yet. And what we are looking here is the von Neumann entropy as a function of the density. And what we see here is in the vicinity of the Mott transition, we see that the entanglement decrease that's shown before. So it decreases, and that's quite consistent, this kind of a thing, if you consider that, let me just plug in here, if you consider that by turning on the interaction, you should really make some of the probabilities less probable by favoring the single occupation probability and favoring the double one and the zero one. And that makes the entanglement also decrease, and that the non-monotonic behavior we saw before. Okay, so that's what we see. Here I'm just giving a zoom in of this regime, more or less, just to say that in all the density regimes, we have this monotonic trend with U. So it's non-monotonic with density, but monotonic with U, always decreasing when I turn on the interaction, okay? So now let's take a look in the other quantity, the linear one, and what we get, okay, a similar stuff here for very high densities. We see a kind of displacement of this of the signature. It starts later on density to appear this difference there, but it's fine. It's still showing the monotonic behavior of interaction. However, if I go to smaller densities, we see here it's a small effect, but we see here that I don't have any more those that trend with the interaction, right? So it seems that, in a sense, this displacement suggests that the linear entropy is less sensitive to the quantum phase transition than the von Neumann one. And to take a closer look in this system, we now vary the interaction for a fixed densities. So on those strong density regimes, so n equal to 1, we see a very nice mapping between the two quantities. So here I have linear, I have von Neumann, and I'm, just in case, I'm also plugging DMRG data to make sure that's not something from DFT, okay? So, and we see they behave well. They have different scales, of course, but the behavior is there. Now, when I go to smaller density, then I see clearly that there is no similar, well, they start to be different. So for this regime here, it seems to be only 1 point, but it's suggesting something, even in the DMRG data, that we do have a non-monotonic behavior. My student is finishing these extra points, of course. But so it's already suggesting something there. And now, and if I go, and this is important because remember I've said that sometimes the non-monotonic behavior of the measure should suggest a quantum phase transition and so on. And here there is no phase transition. And if I was only looking at the linear case, I could be induced to see a quantum phase transition or to understand as a quantum phase transition. But, and it becomes even worse when I go to smaller density regimes for n equal to 0.4. And why is that worse? Okay, the scale is not big, but this is pretty worse because I would see a very different feature where, for example, for the regimes where we have maximum entanglement or minimum entanglement, right? So, oh.
Quick question. This homogeneous change, so the only effect is from the boundaries?
Not even the boundaries. This is Libivu solutions. And then the DMRG, I have chosen 200 sites to compare. So
your LDA for homogeneous should be 10.
But that's not LDA. This is really the exact solution. There's, I have calling DFT. That's something I have to correct before submitting in the paper. Thank you very much, but it's not DFT. That is essentially not DMRG, but this is just Libivu solutions for the homogeneous. Thank you for spotting this. Right. So now one thing we have done, let me see if there's something here. Yeah, so the maximum entanglement end up suggesting some quantum phase transitions where there is none. Then what we have tried is to add in more extra terms in those expansions to see whether we could recover the von Neumann entropy at some point. Oh, but before, sorry, I'm changing right now the order of the slides and I forgot. So in order to try to understand why there is a specific regime of interactions where the two entropies do not match, but in others, yes, we have give a closer look to these probabilities, in particular for the double occupation one. So what we see for this model, specifically in the homogeneous system, is that this double occupation probability is quite sensitive, of course, to the density, right? So it means this curve here is going in interaction. So this is u equal to 0, and here I'm increasing the interaction. And what we see is that we could really look at the system as two specific regimes. One before more or less n equal to 0.6, where this double occupation probability is negligible. So we could simply neglect this term here. And by looking again in our terms, that linear part would be proportional to that, okay? That's one thing. Now, for stronger interaction, for higher densities here, we could then, we could not discard the double occupation probability. And by doing that, that means we would have terms like that. So mathematically, from here, it's clear that the reason for which, in this case, the linear entropy goes well is because this quantity is smaller with the presence of this negative term here. And by that means it's less relevant to throw away higher orders in this case. So that's mathematically. Then when we then include more orders in our expansion, what we get, so here is the case where it was not pretty bad. It's intermediate regime with density equals 0.5. And going up, I'm just plugging one extra order in the expansion. So that's the first one, the linear, 2, 3, and so on. And we see that more or less here, pretty bad. Also asked her to change the colors. But the point is, beyond the fifth order, we can see essentially the same behavior as the von Neumann one. But now if we go to a smallest regime, n equal to 0.2, this takes much longer to be recovered, right? So even the S20 is not enough yet, okay, to recover the von Neumann entropy. So now our question was, okay, so how? This is everything for the homogeneous, exact data, and so on. But now how it could affect things that we have done? And coming from a quantum information community, we have been used so far, the two entropies as equivalent. So now we were interested, are those papers all, we have to go back to those papers, yes or no? And we start to look at that by looking at the disordered situation. And well, here. So here is the disorder chain. And this is how that problem with the linear entropy goes through the inhomogeneous system. And we have here just the three different density scenarios for a specific type of disorder and concentration and so on. But what we can find is that in general, they map to each other. So you should compare, for example, the red and the red in the black and black. These are the two entropies for a given specific concentration here. So they perform pretty well. And our interpretation to this is that in the disorder chains, that doesn't matter much, that difference, because, okay, you start with an average density that is small, but when with the disorder, it's all changed. You have an inhomogeneous density distribution, so you probably have there both scenarios, the scenarios where the two entropies works well and the scenarios where they don't match. So in average, it's fine to use both linear or von Neumann entropy for disorder chains. That is our message in this respect. But when we go to the superlattice structure, that's a different story. In there, we have a much clear scenario, so to say. So we don't have the average typical for the disorder case. In there, we see impact of using one or the other entanglement measure depending on the structure of the lattice. So here, for example, I'm considering three different structures, but I'm showing only two, sorry. I've just chosen two graphics to show, where I have two sites with a certain potential, 7 without that potential, and so on. So that's the periodicity of the external potential. Plug in there with a certain values here. And what we see is that depending on the intensity of this this superlattice potential, we see quite different behavior between them. So for example, the smallest, that's what I'm seeing here. So the smallest is this periodic potential intensity, the worse the behavior, the qualitative behavior between the two entropies, and also the less homogeneous between that potential. So for example, 2.7 is worse for the linear entropy than 4 to 5 that is more balanced in its structure. So I think, okay. All right, so here are essentially our conclusions. So we have, in a first moment, this message that the linear entropy is indeed less sensitive in some cases to the quantum phase transitions than the von Neumann entropy. And the reason is that it may incorrectly predict a quantum phase transition, can estimate regimes of maximum and minimum entanglement incorrectly. In this order, it seems that the average makes the two quantities essentially equivalent indeed, but that's not the same story in the superlattice where we have regimes or where the two entropies do not match. But now that is from the condensed matter point of view. So some results that could give you a trend, an idea of which one of these two measures choose now to analyze your quantum phase transition. But now there is also, in the other way, we could also consider that what we have here in this model is a very sensitive test bed for quantum information tools. So since it, you see, the fact that it's a strongly correlated model gives us a very subtle difference in those entanglement measures. And this could be then used to testing other measures in the model. It seems to be something that could be done. So I would like to thank you all for the attention, in particular my now PhD student, but this is her master thesis. Thank you very much for listening.
Thank you, Vivian. We have time for questions.
Hi, Professor. Thank you very much for the nice talk. I didn't quite understand what is the signature in the von Neumann entropy that gives you the information about the quantum phase transition.
Yes, so the signature alone is not enough. So in those things that I've showed you, there were quantum phase transitions there that we already know that they are there, right? So, and this may differ from system to system. So if I go back there, for example, when I showed in the very beginning, it would be easier. So when I showed this, for example, and so we could see here, for example, we know that there is the mod transition. That means the system becomes localized here at n equal to 1 in the Hubbard model for any repulsive interaction. And the signature in our measure, in this case, is this minimum here. So, but in the vicinity of the phase transition, you expect to see this non-monotonic behavior, right? So that is similar to what we have been using here. But in our case, we try to look either in a quantum phase transition that is pretty known, or we also look at other quantity that can confirm, because looking only at the entanglement might be not enough to see the transition. While here, this is even clearer, I would say, because you really start with a certain degree of entanglement, and as soon as you plug in the disorder potential, what we see is a strong decreasing of this entanglement, suggesting the localized states, the localized phase, localization for disorder case.
Okay, thank you very much.
Hi, Vivian. I wanted to ask, so the linear entropy, some people also call it the Renyi 2 entropy, and von Neumann would be the Renyi 1. I have opinions. It's a family of entropies. I was curious, have you tried like
Not yet.
Seeing if all of them, if maybe only the von Neumann gives a signature.
Yes, yes. Well, the idea now is trying to look at other of them. Yes, because, well, in the beginning, I just thought my student was doing something wrong, and or either DFT is failing somehow. But now that's the idea, to explore other measures and so on.
Okay, thanks.
Any other question? Okay. So let's thank Vivian again.